All right, so I'll do a little bit of a recap, kind of where we left off with things. Then we'll jump into some new material, but before I do that, point out. So we've got that kind of connect and Excel assignment. So the Excel assignment, the very first part of it, we should kind of be able to do already. We thought about how we use that norm.s.dist or the norm.dist function, kind of just dealing with normally distributed data. I think some of the other stuff that's involved in that. So the next 2/3 we'll start to cover today. So you should be able to do problem 1. This is stuff that we'll be kind of working on starting today and then kind of completing for sure on next Monday. And then the end of next week, I go back here, that connect assignment is due as well. You should be able to kind of make your way through the majority of this assignment based off of everything we covered today. And then kind of after class on Monday, I'll likely put up the next connect assignment as well, just so as we're kind of going through things you can start working on. Okay. All right. So I believe we left off kind of going over these examples where I was looking at the distribution of sample means, right? We said we know certain things about these distributions. And, this was the fact that if I start out, doesn't matter if it's normally distributed or not, but whatever my data is that I'm sampling from, I know that my sample means will be centered around that same population mean, and that the standard deviation of my sample means will be just the square root of the original variance over my sample size. Okay. So I think this is kind of where we left off. We worked through a couple of problems to say, okay, if I then have some cutoff value for this sample mean, and I want to know the probability I see that value or anything below it, well, what can I do? I can turn that value into a z value to represent the number of standard deviations away this value was from this mean. Once I have that, it's a matter of looking that up in the table. The table will tell me the probability of seeing that or anything to the left of it, or the area to the left. Okay. So we went over this one at the end of last class, I believe. So we kind of have to put some numbers to this. We're going to have to move on today to, instead of looking at sample means, we're going to look at sample proportions. Okay. So the sample proportion is just a unique example of the sample mean. So if you think about what this might look like, if we had that maternal smoking variable, this would be the sample proportion would be the number of mothers who smoke, or kind of like the number of successes, whatever we're looking for, out of whatever our sample size is, right? So 50 of the 200 mothers in the sample smoke during pregnancy, right? So 50 over 200 in that example, or 0.25 would be our sample proportion. So our sample proportion is always going to be somewhere in between 0 and 1, right? It's not, it's easy to get this confused once you go to the table. So looking at the probability that the table is telling us, those are not the same thing. This is just a very unique case of the sample mean. Because if we think about how do you calculate a sample mean, you added up all the x values and then divided by the number of values you added up. Well, here, if I've got an original variable, which is does the mother smoke or not, that's just a bunch of zeros and ones as my observations. So when I take the mean of that 1, 0 variable, I'm going to be adding up ones and zeros, but the zeros don't impact it at all. So that numerator is really just going to be the number of ones I had for that variable, or the number of mothers who smoke while pregnant. And then divide by the total number of observations that I had in the sample. So the sample proportion is really just a unique case of the sample mean, where we started out taking the mean of a 1, 0 variable. But because of that, we have to treat it a little bit differently when it comes to what its variance is. And it'll kind of present a couple of additional kind of challenges that the sample mean didn't, since it's a unique case. So if we go back to the binomial distribution, we said that if we wanted the number of successes right? Then we had n times p was kind of the average expected number of successes. Well, with proportions, we're not interested in the number of successes. We're just interested in the proportion of successes. So our mean, we kind of think about our sample proportions. Actually, I'll start with the population first. So this, some distribution of the population proportion, it should be centered around whatever that true population proportion is. That should be the most common proportion of successes we see. Just like with the most common number of successes was n times p, we just want the proportion, so it's just p. And then we have the variance of those proportions. Well, before, the variance on the number of successes was n times p times 1 minus p. We don't want the number, we're just looking at the proportion now. So this goes down, so this simply becomes p times 1 minus p. So we're not inherently, like in the other examples, we would have to be given the population variance. So I'm not going to be given the population variance here for proportion examples, but I can calculate it by simply taking p times 1 minus p.
Okay. Wait, what are you calculating p times 1 minus p?
Right, so think about before what I had up here, and I'm going to get rid of this in a second. We had some normally distributed variable, right? And it was centered. You kind of think about the mean of that variable was just the population mean, right? If we can observe that. We had population data, could also come up with what a population variance was, right? Here, sorry. That was like the variance of this random variable x. Now, the variance of this random variable that is a proportion, we won't kind of compute the variance the same way, right? Remember, we had this equation for the binomial that said this will give us our variance. A 1-0 variable, success or failure, is really a binomial where we're not interested in the number of successes now, just the proportion of successes. So that's why we know the variance of this proportion variable will be p times 1 minus. Does that help clear up a little bit? So this is just related to something we already talked about, but we got to keep pushing it, right? So from here, don't worry about this yet. I'll come back to this slide, but I'm going to draw something up here. So we don't need this anymore. Just like with my sample means, my sample proportion, right, kind of using p hat as opposed to p with a bar over it, we know that this should be centered around kind of whatever my population proportion is, or the mean of my sample proportions is the mean of the original population data, right, which was just that population proportion. Okay. Actually, now that I'm saying this, we definitely did one of these examples of last class, right? Because I worked through a coin flip example with you, and then we also did the percent of people who have a college degree. Right? So this is just kind of review because we're going to tackle confidence intervals, which relies on all this stuff. Okay. So similarly, as we were doing before with the sample mean, I might have some sample proportion. I'm interested in finding the probability of being below that value. I'm going to turn this into a z-score, right? Then I can look that up in my table, find the area to the left, right? If I want the area to the right, I can do 1 minus. Now, how do I calculate those z-scores? So they're going to be very similar. I'll kind of leave these up here probably for the rest of the class. So for our sample mean, we said take the statistic we're interested in, subtract the mean of that statistic, divide by the standard deviation of that statistic. We're doing the exact same thing for this sample proportion. It's just now we subtract the mean and the standard deviation of the statistic we're looking at, which is the sample proportion. We said we can break these down a little bit further because the mean of my sample means is always just whatever the population mean is. And the standard deviation of my sample means is just the square of the variance from that population I sampled from over the sample size. Similar down here, the mean of my sample proportions we have over there, it should be centered around whatever that true population proportion is. And then the standard deviation of my sample proportions should just be the variance of that original data, which we now calculate with p times 1 minus p, divided by my sample size. So this is, there's a little bit of differences in how we calculate the z values, but once we have those z values, everything's exactly the same. So we worked through a couple examples with a coin flip. I skipped the second coin flip example, and then I did one where we had like the percent of people who kind of had a college degree. Okay. So a little bit of review, just kind of what we've talked about with these two statistics, so we can jump into confidence intervals. Okay. So 99% of the time, right? I think this whole thing seems kind of hokey. So like, for example, I have a sample mean, right? But how do I know the population variance? Like if I had the population data, I just calculate the population mean. But we have to kind of understand this before we get to the cases where we don't have that. So for now, just assume that somehow someone's telling us that population variance. So 99% of the time, we have no idea kind of where this population mean is. All we can do is base it off of the sample that we see. So we talked about making sure we have a sample that's kind of looks just like the population, right? Talking about bias, things like that. So what are we going to try to do when we make predictions based off of our sample about where the true population mean is, or true population parameter? We can do this for the mean or a proportion. So we want to have unbiased predictors, and we want to try to get as low of a variance as possible. How can I guarantee that I get as low of a variance as possible, or lowest standard deviation as possible? Remember, what's in these denominators? Those represent my standard deviations. So if I increase my sample sizes, that decreases this entire value. So higher sample sizes will allow us to kind of get this decreased kind of variation that we'll see in our sample statistic. So the general setup of what we're going to do with confidence intervals, it kind of relies on the other old stuff that we've talked about. And I'll kind of give a broad idea first, and then we'll break it down to what we're actually going to do. So we're going to start out with whatever sample statistic we see. We're going to go a certain amount to the left and a certain amount to the right to build a range of values where I can say with 90% confidence, the true population mean is somewhere in this range. So how do I choose W, right? Where is that going to come from? Okay, so the general idea is you build this range of values. Oops. Let me see, I know I've got it up here somewhere. There we go. You build this range of values where you can say with a certain level of confidence, the true population mean is somewhere in this range. So what are those values going to be? Well, we can use the fact that our sample means will be normally distributed to kind of understand this. Okay. So let's think about this. So my sample means should be centered around my population mean. Okay. If I think about the area out here, let's say, just for the sake of this example, I think this is what I chose in the slide. So hopefully this is going to match up with what I show you here in a second. So let's say that I thought about what's the likelihood I see something that's this far away from that population mean? Well, if I know the area that I kind of want in the tail, right? Or think about what I'm saying here would be the probability I see something within a certain number of standard deviations above and below, I want to be 95%, right? So I want that probability of whatever these two cutoff values are, I want that to be somewhere in between kind of 95%. So if I work in the inverse, right? And I think about, okay, well, what if I converted whatever these values are into Z values, right? Going the same number of standard deviations to the left and the right. What would that Z value be that gives me 0.025 kind of in each tail, or 0.95 being the probability I see something within that many standard deviations? Well, we can go to our table. Okay, I did choose 0.025, so that's good. Scroll down here. The probability that I have is 0.025. That's exactly this number right here. So that corresponds to a Z value of 1.9. We scroll up, 6. Okay. Excuse me. I'll come back to this once I think seeing you on the board might make a little more sense first. So we just found negative 1.96. Okay. Once I have that value, right, I can think about, okay, if I were to see any sample mean in this range. So we went through from what we knew about standard normal distribution. I can figure out how many standard deviations away I need to go in order to guarantee that the probability I see something in between this many standard deviations above or below is 0.95. That's the probability I want in the middle is 0.95. So if I just take a sample, there's a 95% chance that it's somewhere within 1.96 standard deviations of whatever the true population mean is. So even if I can't observe it, because I know that sample means are normally distributed around this value, even if I don't know what this value is, I know that there's a 95% chance I see something within 1.96 standard deviations above or below. Okay. So from there, I'm trying to think about what we're going to do with confidence intervals. So I know that these values, right, have to correspond to being 1.96 standard deviations away. That's the definition of a z-value. So I can think about it here. I've got just subtracting, right, looking at the other side. So let's say I take a sample and I see a sample mean value that's like right here, right? Not very far away from that population mean. If I were to build a confidence interval around that, right, where I take that sample mean value and I add and subtract the same amount to it. So what that W is going to be is I'm going to say, okay, look, if I go 1.96 standard deviations away, sorry, not minus, plus on that one. If I go 1.96 standard deviations above the sample mean I saw and 1.96 standard deviations below that, well, I can kind of visually see here, this sample mean is definitely like not 1.96 away. So when I build that upper and lower bound, it's going to be guaranteed to include that population mean. If I then say, let's say I saw something over here, right? I see this is my sample mean. I build my confidence interval around that, right? So add 1.96 standard deviations to get my upper bound or the kind of upper limit on my range. And then I subtract that many standard deviations away to get kind of that lower limit or that lower bound in my range. Well, this value is just barely, right? It's not quite 1.96 standard deviations away. So when I add 1.96 standard deviations to it, I'm going to make sure that that upper limit includes that true population mean. Right? So any value that's within 1.96 standard deviations of the mean, when I create the confidence interval for it, I'm guaranteed that it's going to include that true population mean. Okay. Now, what happens if I was going to see something way out here? Well, this value is more than 1.96 standard deviations away. So when I create my lower bound here and my upper bound, so I subtract 1.96, I'm not going to quite make it back to whatever that true population mean is. This confidence interval wouldn't include the true population mean. Okay. So this is the idea behind what we're doing with confidence intervals, is that we know we only observe usually one sample. All right. But if I build a confidence interval around that sample mean by going whatever number of standard deviations kind of corresponds to the probability that I want in the middle of that distribution, we'll just kind of call it that for right now. We'll have another way to think about it here in a second. That 95% of the time, I'm going to have a sample mean where when I build the confidence interval, it includes the population mean. So when I build my confidence interval, I'll be right 95% of the time that the true mean is somewhere in that range. Anytime I see a sample mean over here or over here, well, that's going to be a sample mean for when I build the confidence interval around it, it wouldn't include the true population mean. So if I'm only able to observe one sample, I know that I'll be right with a 95% likelihood, but that also means I could be wrong with that 5% likelihood. So we're going to base kind of our confidence interval around our sample mean because we only observe one of these. right? But you can imagine if I was able to kind of continue to take sample over sample, what I would end up seeing is that, out of 100 samples, 95 of them would have a confidence interval that included the true population mean, if I could observe it. And then 5% of them would have a confidence interval that didn't include the population mean. Okay. So, this is what I have up here on the board, but you can imagine any sample mean value in this blue range has a confidence interval that includes the true population mean, right? It's within that interval. But then 5% of the time, we're going to end up with one of these sample means out here in this red area, where we build a confidence interval around that, it wouldn't include that true population mean. So the equation that we're going to have for our confidence interval, I'm skipping ahead here for a second, is going to look something like this. Okay. So I'll go back, right, to the previous slide here in just a second. I want to kind of make a point here. So before I had an actual value of 1.96, that corresponded to a certain Z value, or that was a Z value. Now, we'll talk about alpha in a second here. But for now, just know that this Z value is just going to be something that we look up in the table. It's going to be the number of standard deviations away we need to go to build our confidence interval based off of whatever level of confidence we want, right? Whatever probability we want kind of there in the middle. Right? So once we know how many standard deviations away we need to go, well, that doesn't tell me what my values for the original sample mean would be. Like if I was, let's say this is 1.96. Well, if the standard deviation is 10, that means I need to add and subtract 1.96 times 10 or times whatever that standard deviation is. If the standard deviation is 100, well, then I need to add and subtract 1.96 times 100, right? So we'll go take our sample mean, we'll add what we'll call here is the margin of error. And if you ask a statistician, they're going to tell you this isn't technically correct. They should only use that term with proportions, but it makes it easier to talk about it across all the examples we look at. So think about this number of standard deviations away I want to go times whatever the actual standard deviation is. That represents my margin of error. When I add that to my sample mean, I get my upper bound and my upper limit. When I subtract that margin of error, I get my lower bound and my lower limit. So I'm shorthanding this. You could really think about this as representing two equations. One where I add that margin of error, one where I subtract it. That should give me kind of that, just like I have over here. That should give me my kind of lower bound and my upper bound.
Questions? Yes. So when we're finding all this out, we're finding the sample mean is based off the population mean. Other than when we're doing confidence intervals, in which the sample mean would be given.
So the sample mean will always be something that we're observing from our sample, right? So let's say I go out, I randomly select 50 people to record their image. I can calculate my sample mean. That's all I can see. So this will be something I'm calculating from data. I will never observe the true population mean. The whole point of what I'm doing in my sample is I'm trying to get an idea about where that population mean is. But the best guess of that I have of where that is whatever I saw from my sample. So if I then take what I saw from my sample and add and subtract this margin of error to it to create this range of values, I'm guaranteeing with, in this example I was using before, 95% confidence that confidence interval will include the true population. Now, I don't know what the exact value of that population mean is, but I know it's somewhere in that range.
But for sample Z scores, we have to base the sample mean off of our population mean given. Isn't that what
Yes. So we're going to have yeah, let's see what you're saying. Yeah, we aren't going to be able to convert these sample means into Z values. We were only able to do that when we could also observe the population. But knowing what those Z values represent, we don't need to know exactly which one of these sample means that we have. We just need to know that if we go out 1.96 standard deviations above and below, that's going to guarantee that our confidence interval includes the population. So we can't convert these sample means into Z values anymore. That's what you're kind of getting.
It's more like exam prep. If we're asked to find the
Gotcha.
sample Z-score
Gotcha. Okay.
comparatively to this confidence
Yep.
interval.
So you would have to be asked something like, you'd be giving a cutoff value, kind of like in these, go back. It'd have to be something more like, if we had a weight plate example. There we go. All right, so. Have here, there, come on, all right. So we had the birth weight example, right? So this would be something where I would have to tell you the population mean and the population variance in order for you to convert a value for the sample mean into a z-value and then find the probability you would see that value or anything below or above, depending on the question. So I'd have to directly give you what the population mean is. If I don't tell you what the population mean is, you know, and the question on the exam, like, I'll get those practice exams up after class today, but it's, you know, I'm gonna be asking you for what the confidence interval is. Like, so be very direct about like, here's the sample mean you see, you need to build a confidence interval around that.
Would we need to do something like that, however?
Yes,
Yeah.
yeah, this could be a question too. All right, now. If I ask you a question like this, where I've given you the population mean, that's gonna be your indicator that you are able to convert this into the z-value. And then find the probability being above or below whatever cutoff value, in this case 39.5. So, going through here, examples, values, and go help with the percent. So, we're building these confidence intervals because we want to know where that true population mean is, but we can't observe it. So, one other thing that we have to talk about from this equation is what is this Greek letter alpha? Okay. So this Greek letter alpha, the easiest way to kind of remember or think about what it is it's the percent outside of whatever level of confidence I want to say in decimal form. So, for example, when I wanted to be able to say something with 95% confidence, that area in the middle is 0.95, 5% is outside of my confidence interval. But if I've got two sides, right, an area on the left and an area on the right of my confidence interval, I'm going to have half of alpha in each tail. So when I have a 95% confidence interval, what would the percent be outside of it? 5. In decimal form, alpha would be 0.05. But then when I go to look up that z-value, how many standard deviations away do I need to go when I'm building this confidence interval? Well, I've got two tails, so there's half of alpha in each tail. So now that I know that I want alpha over 2 in that lower left tail, I'm using the inverse process where I know the area in the tail, I'm working backwards to find the z-value. So I knew that I wanted 0.025 in that lower tail. I looked it up in the table and found that z-value was 1.96. We could do this for, you know, whatever alpha we want, but that was just one example. Yeah.
So if it was 0.5, would it be 0.25 for the left side and the right side?
Point.
Are you just like splitting it in half?
Yeah, I'm just splitting it in half, right? Because we know this is a symmetric distribution. And I know that if I'm going the same number of standard deviations to the left and to the right, so like this is going to be 1.96 standard deviations above and below, these areas have to be the same. So the total area in them will be alpha, right? So if I was a 95% confidence interval, the total area in there will be 0.05. But because I have two equally sized tails, the amount that's in each one of those tails would be half of alpha or 0.025.
So you're finding alpha as a whole and splitting it in half?
Yes.
And will that confidence level be given to you?
Yep.
Usually.
You would have to be able, like, if I asked you to build a confidence interval, I'd have to say, you want to build a 99, a 95, or a 90% confidence. Once I tell you what level of confidence you want to say this with, you know, okay, what percent would be outside of that confidence interval, 1, 5, and 10%, in decimal form, 0.01, 0.05, 0.1. Now you could work the other direction as well, right? If I told you, so that was kind of what I just explained, I give you the confidence interval, you can work to the alphas. If I tell you the alphas, well, you know that's the decimal form of what's outside your interval. So let's say I gave you an alpha of 0.2. What confidence level would that be? So if I've got 0.2,
0.0.
yeah. So, and here's where it gets a little tricky because kind of going from alpha, which is decimal form, to confidence level, which is in percentage format. 0.2 would mean that there's 20% outside my confidence interval, which would mean my confidence interval, or what's within my range, is 80%. If I had 0.07 as my alpha, what would my confidence level be? 93%, right? 7% outside means there's 93%. So you can work in either direction. I can give you alpha and you would kind of know what confidence level that corresponds to, or I tell you a certain level of confidence and you know what the corresponding alpha is. So we'll come back to this slide after we work through an example. Okay. So here's my equation, right? I can actually rewrite this a little bit. Now, the way that I'll work through these, I'll break it down to steps so this thing gets easier to not make a mistake. But right, we had an equation for the standard deviation of our sample means. We said that was just the square root of the population variance over my sample size. So all I'm doing is kind of substituting that in. Now, what I could do is find this ahead of time, then I would just have one value to plug in. That's right. I can do this either way. I can break it down to steps or I don't have to. I'll kind of show you what both of them look like in this example. So let's say I've got a production process. So it's going to seem kind of hokey at first today because I'm going to be giving you population variances, but like you don't know the population means. So how does that happen, right? So to give you a practical application of how this could happen, think about it as though I'm making these hockey pucks, right? It's being poured into, a bunch of materials, a mixture of materials are poured into a mold. But the problem is that mixture of materials isn't always the same. So some hockey pucks will weigh a little bit more than others. Some of them, might be a little heavier, might be a little lighter. I know based off of like, I don't know, shows that this is not my wheelhouse, but like the chemical composition of whatever materials I'm using, I could figure out what the variation would be on my machinery, on that production process of pouring into the molds. So often this is going to be something like, I know my machinery has a certain level of variance on these pores that it's making with these hockey pucks. So I know the population variance, but I can't sample every single product I make. I might only be able to sample what? How many? 49 of them. So I pull 49 of them off the assembly line. I know that my population variance on the machinery is, I don't think I give it to us here. What did I want? Oh, no, I must have given it. Where is it at? I'm just not reading it right. Oh, it's the first thing. Has a variance of 49 grams. There you go. All right. So I'm told that the production process has a variance of 49. I then took a sample of 49 different hockey pucks, and I calculated the sample mean to be 7.5. From here, it's just a matter of plugging our values into this equation, and then we'll have one added step. So initially, right, my sample mean is 7.5. I'll have to find the Z value. But there, I'm just plugging in my sample or my population variance and my sample size. Now, this is where I can calculate this ahead of time. So for instance, if I'm trying to do this equation all at one time in a calculator, square root of 49 over 49, maybe I do something wrong with my order of operations. This is pretty easy to do on its own. So 49 over 49 is 1, the square root is 1. I could just plug 1 in. But, with different values, you can take this approach as well. But I always kind of say, like, break it down, like, calculate that standard deviation so you just have one value to plug into that equation. So the last thing we need is that Z value. Well, if I have the 99% confidence interval, the fourth thing that we'll need to identify in these types of examples where we're building confidence intervals is alpha. Here, for the 99% level, my alpha should be 1% is outside, so 0.01. Now, what this equation will kind of remind me of, if I don't have the nice visual, is that, well, alpha is the total area on both sides of that distribution, right? So if there's alpha total in the tails, half of alpha is in each one. So I want to find the Z value that has what? 0.005, right, in each tail. So I have to use my standard normal table to do this. I know the area that I want in the tail, kind of like we had over here. It's no longer 0.025. Now I want 0.005, which means I'm not going to have the same Z value for this level of confidence. I need to actually look up and see what Z value would correspond to that probability that I now want. So I go to my table, look up 0.005, right? That's the probability I want. Looks like it's kind of in between these two values. It's the closest I can get. So negative 2.57, negative 2.58. Just like we were doing before with the earlier problems, when we're calculating this, we'll always kind of use the higher of the two. So when we look up that Z value in the table, because we're dealing with high levels of confidence, 90, 95, 99, alpha is always going to be 0.1, 0.05, 0.01. When I divide that by 2, I'm getting really small values here in that left tail. So when I'm looking up something, that's below 0.5 in terms of the probability that I want, I'm always going to have negative Z values. So when I look the Z value up in the table, I'm always going to find the negative value. But that positive and negative are already built into my confidence interval equation, right? I want to go 2.5 standard deviations. Sorry, 2.58 standard deviations above to get my upper bound, and then 2.58 standard deviations below to get my lower bound. So even though I see the negative value in my table, I'll have to remember that's kind of already built into this equation, right? I'm using the table to find that value at 2.58. Yeah.
So you would find the negative answer and the positive answer?
So you don't have to go through and do it for both, right? Because inherently, you want to go the same number of standard deviations above and below. So once I have the negative Z value, I automatically know it's the other Z value is just the same, but positive, right? I'm wanting to go 2.58 standard deviations above to get my upper bound, 2.58 standard deviations below to get my lower bound. Is that?
So it's basically the same answer for both sides. You just put
Yeah,
negative.
it's going to be the same number, just negative and positive. Because if I want the same area, right, each of my tails, we said they're the same size. So 0.005, 0.005, we know the standard normal distribution is symmetric around that mean of 0. So this is going to have to be the exact same value if the areas are exactly the same. So we found that 2.58. All right. We identified, here's kind of the general steps. Identify the information you're given. For the sample mean example, it's going to be a sample mean, a population variance is going to have to be told you the sample size, and you're probably going to have to figure out what alpha is based on the level of confidence you want to build this confidence interval for. You then have to use alpha, think about half of alpha on each side, look up the Z value that corresponds to that. I can do the intermediate step. I said calculating the standard deviation of my sample means. Right? I can either kind of create another step where I calculate that and then just have one value to plug in, or I can do it all at once if I really want to. I can kind of skip step 3 and kind of build it all into kind of that final step 4 if I really want to. I think it's just a little bit easier to think about these things if we break it down into parts. So for us, we identified the piece of information we're given. We looked up that alpha over 2 value. Now it's just a matter of getting everything plugged into our equation. Okay. Question on this one. Yeah.
So you think it's best for us to memorize alpha, like for the percentages and stuff?
Yeah, honestly, as we work through more of these examples, I think it'll become kind of second nature because alpha is always we're going to look at 3 main benchmarks. So it kind of makes sense. The 90% confidence level, the 95, and the 99. Well, those are always going to have the same 3 alphas, 0.1, 0.05, and 0.0. So yeah, you kind of are memorizing them, but I think just as we see those happen over and over and over again, they'll kind of become second nature. So let's work through another one. Actually, do I have another example here? So I think this one makes a little more sense. So I want to try to give you a little bit more of the understanding of the usefulness of a confidence interval, right? In terms of a decision-making process. So I'll leave this up here and we'll kind of work on the other side of the board. So let's say I had this example and I'm trying to figure out, this kind of sounds like a stupid example, but I'll make it, hopefully will give you some examples that show you this could actually be very, very useful. But the original example will seem kind of stupid. So let's say I go over to the rec center and they've got all these 45-pound weight plates and I take a sample of 35 of them. So my sample is 35, sample size, sorry. I then calculate the sample mean of those 35 of those 35 weight plates, or those 45 pound weight plates, and find that the sample mean is 46.5. Right? So, same kind of idea with the hockey puck. When they're pouring these out, if it's made up of more than just one metal, there won't always be a uniform pour. So if you actually go over to the rec center right now and you start weighing them, you'll find that some of those 45 pound weight plates are 47 pounds, some are 44.5. Some of them are, they kind of, they're close to 45, but there is some variation. Right? Now, I would have to tell you then, this is not something you could inherently know, but I contacted the company and they tell me that based off of, chemistry and physics, the way that this machinery is pouring these, that the variance on their production process is 25 pounds, right? Or there's a population variance of 25, okay? So if I want to build a confidence interval where the alpha is 0.1, so what would my confidence level be for an alpha of 0.1? 90%, right? So 0.1, 10% outside the interval, 90% inside. Right? So what I'm going to do is I'm going to think about, I've got all the information I was given. Actually, I forgot to write down the last one, which was what? Alpha is 0.1. I need to then find that Z value, right? I've got everything I need to plug into that equation. Like that's just always going to be given to me, right? Now, when we get to some Excel examples, which I should be able to show you some of it today. We're calculating the sample mean and the sample size on our own, but we have to be given that population variance. Okay. So now that I know I want 0.1 total, kind of outside of my interval, what Z value would correspond to that? Well, I'll have half of alpha on each side, right? So 0.1 over 2 or 0.05 on each side. If I look that up in my table, what do I find? So I have that probability of 0.05. If I look that up in my Z table, what Z value corresponds to that? Anybody want to help me out?
Negative 1.65.
Yeah, so if I go to that 0.05 in the middle, I think I can find that, I'm in between two values, which is in between negative 1.64 and negative 1.65. So that Z value we find is 1.65. So how I was doing that, just trying to motivate you guys to kind of try to look it up on your own because it's just getting more practice using this. But I want 0.05. I'm in between these two values. So negative 1.64 and negative 1.65. We'll use the higher of the two. Okay. So now that I know how many standard deviations away that I want to go, right? It's just a matter of plugging everything into that equation. I'm going to break it down into parts. So I'm going to first calculate that standard deviation of my sample means. That's just going to be the square root of that population variance. So I've got the general equations over there over my sample size. Right? So I'm going to cheat here. We identified everything we were given. We looked at that Z value. So 0.8452. And then from there, it's just a matter of take my sample mean, subtract my margin of error to get my lower bound, add my margin of error to my upper bound. So I'll write this out in kind of two equations just to help maybe this make a little more sense. I want to go 1.65 standard deviations above and below, get my lower and upper bounds. I then need to multiply that by, well, if I want to go 1.65 standard deviations away, what's my standard deviation? So I need to multiply that by that standard deviation that I calculated.
So you wouldn't multiply by half alpha?
Nope. So when I'm writing this out, using this as a subscript, I'm just trying to identify this is the Z value that corresponds to having half of alpha in the tail. So this isn't like multiply Z by alpha over 2. This is just saying we need to look up the Z value that would give us alpha over 2 in the tail. Is that?
And that 1.65 is from like where you found that, and then
When I went to the table, I found half of alpha, which is 0.05 or as close as I can get to it. Found the corresponding Z value. Then I plug that Z value in. Now I could have not broken this down into parts. Notice here, instead of multiplying by the standard deviation of my sample means, I could have done this all at once and just plugged in the equation for that into the other formula. But I don't know, I just think it's easier to kind of break this down into parts. Because it kind of makes sense, like I'm gonna take my sample mean, and I'm gonna go a certain number of standard deviations away. I want to go 2 standard deviations away, how far away is that? 2 times whatever the standard deviation is. So this I would call kind of like my lower bound, when I subtracted my margin of error. When I added that margin of error, I call that my upper bound. Right? So if I go ahead and I plug those values in, right, I get something like this.
So will those numbers be different
What numbers?
for the lower, on the left side and the right side?
Yeah, right, because if, think about this, if I take 10 and I add 5 to it, I'm getting 15. If I take 10 and subtract 5, I'm getting 5, right? So even though we're adding and subtracting the same amount, that's why I wrote it out over here as 2 separate equations, because this really is 2 separate equations. I'm just shorthanding it because they're the same values. The only thing that changes in my lower and upper bound calculation is I'm adding that margin of error to my upper bound and I'm subtracting it to my lower bound.
You don't need to use alpha. Once you find it to the.
The only reason I need to use alpha is in the process to look up that Z value.
So that's what that Z A slash or it's how do we.
Yeah, so it's hard to subscript these in PowerPoint easily, but like this is supposed to be the Z value that corresponds to having alpha over 2. I think maybe when I'm writing it out here, I do a slightly better job of like making it smaller to kind of show this.
Okay, cool.
So I've got this range of values, right? We said alpha 0.1 corresponds to a 90% confidence level. So what is the usefulness of this confidence interval or confidence interval more broadly? Well, once I have my upper and lower bound, what I can go back to this company and say is, look, based off of what you told me your variance is in the process of creating these weight plates, the true population mean is somewhere in this range of values. I don't know where it is, but it's somewhere within 45.11 and 47.89. And I can tell you that with 90% confidence. So why might that be interesting to that company? Well, because your true population mean in your production process, right, is not 45 pounds, which is what you're marketing this product as weighing. Now, this is going to be really stupid and trivial when we're talking about weight plates. But if I'm thinking about a company I'm producing, I don't know, steel beams for skyscrapers, I want to make sure that I'm definitely getting whatever average weight I need that steel beam to be. Or another really practical application, when pills are created, right? So same kind of idea, like when you take a pill, it's not all strictly that drug, they've got other kind of additives in there. And so I want to make sure that my average pill is having whatever my desired amount of that product is in. So I could sample maybe 50 of the pills for my production process. I can't sample every single one. I can't get the population data. As long as I know kind of the variation in that machinery, that population variance, I can start to figure out, is my product actually getting a true population mean of whatever I'm targeting, whatever pounds I want this product to be, whatever amount of the drug I want in this product. Bunch of other examples we can think about, but there's kind of a few to kind of envision what we could do with this conference. Questions on? All right, so we want to show you how to do this in Excel. Back here, but we'll skip an example. There's a couple of things I want to tell you before you guys. So we went through the hockey puck example. Let's say instead I wanted you to do kind of a birth weight example, right? So let's say I give you these 4 values. Okay. I want you guys to get a little bit of practice doing this yourself, right? We've worked through a couple now. So I want you to find the upper and lower bound for this example. So you go out and you sample 81 different births, and you find that the average length of pregnancy or the sample mean from that sample was 38. So you get your sample mean, you got your sample size. You are then told that the population variance based off of what we've seen over time on the length of pregnancy is 9 weeks. So you've given a population variance. And then you're asked to find the confidence interval for the 95% level. So I'll kind of help you out a little bit. For the 95% confidence level, what would your alpha value be?
0.95 or 0.95?
So 0.95 would be what's in your interval. Alpha, remember, is what's outside of it. So 95% confidence level, alpha would be 0.05. So I'll give you guys a little bit of time, talk to people around, work with others. I shouldn't have to be so super quiet. You want to find the Z value that corresponds to alpha over 2 on each side of your confidence interval, and then kind of use that general form of the confidence interval equation to come up with what the lower and upper bound are. Now, I didn't repeat any values here, so really, once you find the lower bound, or once you find the upper bound, you can identify what the correct answer would be. So I'll give you guys a little bit of time to work on this, and we'll kind of go through this together.
So when we do like the variance divided by the sample, we take the square root, actually,
So just to, I don't know if this is gonna be your question, but you're taking the square root of the entire fraction. So you're not taking like the square root of 25 and then dividing it by 35 here. You're dividing 25 by 35, then taking the square root of that. All right, so if you haven't gotten an answer in, take your best guess here, and then we'll kind of go over it. All right. I think I counted 17, so I'll kind of wait here just a second. All right, I think I got everybody here. I'll close it out. So let's kind of walk through this, right? What do we need? We have the general forms of the equation over there on the left-hand side of the board. So let's just first start out identifying what we were given. All right, what's our sample size here? 81. Sample mean we found was 38. Variance was 9. And I told you alpha should be what? 0.05. We really have everything we need here to plug into that equation already, other than we have to look up that Z value, the number of standard deviations, the way we need to go. So visually, we can think about, you don't have to draw this out every time. I'm just kind of doing it since we're starting out to kind of really reiterate this point. But we're really looking for the Z value that corresponds to having alpha total in our tails or half of alpha in each tail, right? So if I've got half of alpha, sorry, my 2's and my alphas sometimes look similar, but if I've got half of alpha in each tail, 0.05 over 2 is 0.025. So when you look that up in the Z table, what was the corresponding Z value that you found? Yeah, and we actually found this earlier. So this is where I said, we're using the same levels of confidence. We're going to see the same Z values start popping up over and over again. Because anytime I want the 95% confidence interval, alpha will always be 0.05. So half of alpha will always be 0.025. When I load up 0.025 in the table, I'm always going to find the exact same value. Right? So from here, it's just a matter of taking our sample mean, subtracting our margin of error to get the lower bound, adding it to get our upper bound. We're going 1.96 standard deviations away. And then this is where sometimes doing the intermediate step, so I only have to have one value to plug in. I could plug 9 over 81. I think this is 1/3. Right? And that should allow me to kind of come up with whatever that upper and lower bound are. I don't know off the top of my head what that is, but if we plug those values in, you can get 37.35 to 38.65. Any questions kind of over any part of that process?
So I got I ended up with 38,
So you went out,
I got 1.64.
oh, I see. So that was. So what did I say whenever we're in between two values? Oh, so you took 1.64. Never mind. We're in between. So what you did is you didn't look up alpha divided by 2. Right? You just looked up alpha. So if you looked up the area of 0.05 in that table, you would have found negative 1.64 or negative 1.65. The problem that we have to remember, and the equation kind of reminds us of this, but we want to find that Z value that corresponds to having half of alpha in each side, which would make a total of alpha combined. So we'll start out with alpha. We have to remember that when we go to the table, we should be looking up alpha divided by 2. So that was kind of where you went wrong.
0.0025.
So we should have been looking up 0.025. Yep. Any other questions on any part of this process? So how do I want to go about this? So I'm gonna briefly go over a slide that I skipped, and then we're gonna look at Excel for the last little bit of the class. Okay? So we go back here. I think. Well, where was it? There we go. What changes our confidence intervals? Okay. So there's 3 things that could kind of change these confidence intervals. Think about each one. Right? So the first one is, if I want to say things with a higher level of confidence, well, even if we just use the examples that we went through, when we had half of alpha be 0.005, I think that was what, negative 2.58. When we wanted half of alpha to be 0.025, that was negative 1.96. And when we wanted half of alpha to be 0.05, that was negative 1.65. So notice, when I want to say things with a higher level of confidence, what's happening to my alpha value? So 90 to 95 to 99, alpha is becoming, so from 90 to 95, alpha goes from 0.1 to 0.05. So it's getting smaller, right? If I want to say things with a higher level of confidence, alpha is getting smaller, so inherently alpha over 2 will be getting smaller. If I want a smaller area in my tail, I'm going to have to go a further number of standard deviations away. So by saying something with a higher level of confidence lowers alpha, that leads to a higher Z value. Right? So higher level of confidence, so I don't know, maybe think about here. When I want to say things with a higher level of confidence, that's going to decrease alpha. As I decrease alpha or alpha over 2, right, that's going to increase my Z value. Now, when I say increase, if it's negative, right, it's increasing in magnitude. It's going to become a larger negative value, right? I need to go a further number of standard deviations away. So whenever I want to say things with a higher level of confidence, just kind of intuitively, if I want to tell you with 90% confidence the true mean is in between these 2 values, or with 99% confidence, I'm going to tell you it's in between these two. Well, to be able to say it with a high level of confidence, I'm going to have to include more values or make my interval wider, right? But inherently, you can kind of see, my interval will be wider if I'm using a larger Z value. I'm adding and subtracting a larger amount to that sample mean. I'll end up with a wider confidence interval, which is not great, right? Because we want to be able to narrow down where this population mean is. If I tell you the true average income is somewhere between 50 and 100,000, that's not very helpful, right? I want to try to be able to pinpoint this down and give you a range of like 500, right? So when I want to say things with a high level of confidence, it's expanding my interval, right? So how can I combat that? Well, the other thing we can change is let's think about what if I took a higher sample size? What's going to happen to my confidence interval there? Well, a higher sample size should reduce this fraction or reduce the standard deviation on my sample means, right? Having more observation just allows my sample mean to be kind of more reflective of the population as a whole. So by taking a higher sample size, I'm decreasing this fraction of that standard deviation. So I'm adding and subtracting a smaller margin of error. So a higher sample size actually, you can kind of think about, gives me this more narrow, right? Or a kind of smaller range of value. So if I want to say something with a high level of confidence, I know that's going to expand my interval, but how can I combat that? Taking higher sample sizes to reduce that interval. Okay. Now, the third one, we don't waste too much time on because we don't really have any influence over what the population variance is. But if the original variance on the data was higher, our confidence interval is going to be a little bit higher as well. But we can't really change that. So we don't focus on it too much. Okay. Any questions over these? And it kind of works in the other direction as well, right? If I want to say things with lower levels of confidence, or if I take smaller sample sizes, everything just kind of flips. So we'll see some of this play out. So I have a, excuse me, file up on, did I close it on accident? I have a file called median rental price. I think I accidentally saved it and then closed it. So if it opens weird like it just did, it's kind of a pain on the laptop to scroll. You can always hit your home key and it should send you kind of back to the beginning. I originally had this data set. It had average rental prices for like the last 10 years, every single month. It was a lot of columns. To make it easier, let's just kind of look at the most recent data that it had, which is the end of 2019. Okay, so this is right before the pandemic. Might be kind of interesting to look at what rental prices look like across pretty large cities, but not all of these are that large. And I think I've got, like 1,700 here, right? So we have a huge sample size of cities. I'm going to zoom in and we can kind of think about how we could start building a confidence interval for where the true population mean rental price in these cities is. Right, or across cities are. So what are the components that I'm going to need? So the first thing we can think about is my sample size and then my sample mean. Okay. So how would I find my sample size? What equation in Excel could I use here? Yeah, so this is just the basic count function, right? Count the number of observations. So I select the first cell, Control Shift, Command Shift on a Mac, hit the down arrow. Another shortcut, if I've got a huge data set like this, instead of scrolling all the way back up and closing my parenthesis, if I just hit Enter, closes the parenthesis for me and sends me back up to the top. Right? I'll then use the average function to find the mean, select the whole column. Once again, Control Shift, Command Shift on the Mac, hit Enter to close the parenthesis and send me back up to the top. Okay. So I've got my sample mean, my sample size, and this is where it gets a little hokey. I'd have to tell you what the population variance was on rental prices. Now, eventually we'll end up seeing if we don't have the population variance, we can do something a little bit different, but we got to walk before we can run. So for now, we're just starting out with examples where we assume that we're given a population variance. So let's say, and I think that this is a number that makes sense. Let's say this was 2,000, okay? But I have to give that to you, okay? So I now have three of the things that I need. The only other thing that I need to build confidence intervals is, well, what alpha do I want? What level of confidence do I want to build this interval for? Well, I can actually build a confidence interval at all three levels, right? So I'm going to start out here and thinking about, I've got 3 different kind of benchmark levels of confidence. Now I could do this for any level of confidence. In fact, I'll throw one down here. I don't know. Actually, I'll throw one down here that's kind of weird, just to kind of prove that we can do this for anyone. So here, my alpha values be what? 0.1, 0.05, 0.01, and this one would be kind of weird. This one would be what? So 87.5% confidence interval. Yeah, so I'd have 12.5% outside of it in decimal form, 0.125. Okay. I'm going to break this down into parts. You could do all of this in one cell, which I think next class I'll have an example where I show you that. But for now, let's just break this down and we'll create a column where we find the z-value associated with each of these alphas. So remember what we're doing when we're finding the z-value is we were just looking up alpha divided by 2 from our standard normal table, right? Well, we already looked at a function like this in Excel, which was if I'm using the standard normal distribution, norm.s, and then I'm starting with the probability, I'm finding the z-value, so I'm going in the reverse process or the inverse, so norm.s.inv. Then what probability do I want in each one of those tails? Alpha divided by 2. It's easy as that, right? So instead of using the physical table, Excel is kind of looking it up in the table for me, whatever that alpha over 2 value that I wanted was. Okay. Now, what's going to be the problem with this is that, oh, yeah, it's always going to be looking at that lower left tail. I'm always going to get the negative values. When I eventually use Excel to be my calculator to build a lower and upper bound, I just want to know the number of standard deviations away I need to, the number of standard deviations I need to subtract to get my lower bound, and the number of standard deviations I need to add to get my upper bound. So I really don't want that negative sign there. So what's one really easy way to get rid of that? We have this absolute value function in Excel, which is just ABS, and then you put parentheses around whatever you want to take the absolute value of. That'll just drop our negative sign to kind of deal with this, the fact that the positive and negative sign are already built into those equations we have for the lower and upper bound. Okay. I could then copy this down. Now I've got my z-values. Notice we can be even more precise. So before when we had to do 2.58, we can get real precise here out to whatever decimal we want. It's not actually 1.96, even though that it looks like that in the table, but it's because we're constrained to 2 decimals. It's actually a little bit lower than 1.96 for that 95% confidence level. So Excel allows us to be a little bit more precise. Yeah.
It was ABS, you said?
Yep. So just ABS for absolute value. Yep. Any other questions up to this point? Okay. So now I want to find my lower and my upper bound. I'm going to kind of create the intermediate value. So instead of putting all of this into Excel, I'm going to find that standard deviation separately. So I just have one value to deal with. So the standard deviation of my sample means was just the square root. So SQRT was the function we had in Excel for that, of what? My population variance divided by my sample size. Right? So I can kind of calculate that intermediate value in between. Right? Now all I have to do to get my lower bound is take my sample mean, subtract the number of standard deviations away I want to go, multiply by whatever my standard deviation value is. So at this point, I'm just using Excel to be my calculator. There is a confidence.norm equation that you can kind of use in Excel. Almost nobody, at least when I've had them use it before, uses it correctly. So I just teach you how to do it this way. It's a lot easier. It's a lot more straightforward. It matches up to how you kind of do it by hand. So when it comes to that homework, don't try messing around with that confidence.norm equation. I mean, if you do and you use it correctly, I'll give you full credit, but I'm not going to take the time to show you because it's a lot more difficult than just kind of setting it up like this. Okay. Now, when I copy this down to get my lower bound for the next levels of confidence, the only thing that should be changing is my alpha value and the corresponding z value. So I'm still basing it off the same sample mean, and my population variance and sample size hasn't changed, so neither will that standard deviation on my sample means. So I'm going to freeze those cell references. So that's F4 or Command T on a Mac. but I'm not going to freeze that Z value cell reference because when I copy this down, I want to keep using the Z value that's associated with each of these next levels of confidence. Okay. So now when I copy this down, notice it keeps using the same sample mean to base my confidence interval around. It's using the same standard deviation, but it's updating that Z value. Okay. Now from here, I'll kind of show you what I think is the easiest way to just copy this over. So I know that for my upper bound equation, I want the exact same thing I just typed in, but instead of subtracting my margin of error, I'm going to add it. Well, the problem is if I copy this over, oh yeah, now updates my cell reference. That's not what I wanted. So that's a pain. So if you want to copy something over and you don't want to change anything in that equation, you don't want the cell references to update. If I double click on that cell, it'll show me the formula. And then going to highlight it and copy it. Hit enter to get me out of the cell. Paste it over here. Now notice none of those cell references changed. But I did want to change something in this formula, which was I now want to add my margin of error. That's kind of a nice, easy way to copy and paste without the cell references changing. Now when I kind of drag this down, I've got my 4 confidence levels or 4 confidence intervals pretty quickly. Okay. Anybody want to see any of those cells again? All right. So we'll go over an example like this for proportions. We'll do confidence intervals proportions on Monday, as well as how to use in Excel. But a couple more things I want to say before we get out of here, but I'm just kind of mentioning that now. As we work off this data sheet, I'll keep like putting up, I'll call it median rental price in class, and I'll just keep updating it as we do more and more work on it, right? So one thing I wanted to kind of point out here is if I had these confidence intervals, I could turn around to some company. So maybe there's a company in there saying, look, putting out there that the average rental price in America now is $2,500. Based off my confidence intervals, I can go to them and tell them with 95% confidence, no, it's not. Right? Because with 95% confidence, I've actually narrowed down the range of values to within a $5 range. So I wanted to make this point with this data set. My sample size is huge here, right? So when I'm building, or, my sample mean should be more informative about where that true population mean is. So when I'm building my confidence intervals, I can get these really, really small intervals, which then make me able to rule out a bunch of values, right? There's only about, a range of 5 for values that could be the true population mean here. Now, notice if I only had, 39 observations instead, didn't blow up that much, but I'm now getting values in a kind of range of 30 or 40. And, if I had higher variance here, so maybe let's say instead of 2,000, this was 20,000 as my population variance. Well, now I'm getting even wider. Right. So having that higher sample size using that count function allowed me to get these pretty narrow confidence intervals. Okay. All right. So this should allow you to kind of get started on that next question on the Excel. We'll do proportions on Monday. And then probably introduce the next type of distribution, which is the student T. So I'll be putting up a student T table under the files tab that, just like the standard normal, I expect you either print it out and have it in class, or you have some way of pulling it up on a computer or phone. Okay. All right. I will see you guys on Monday. Fun, safe,